Okay, so for this assignment, I decided to work with a bowling ball viscosimeter. The setup of a falling ball viscosimeter is as follows. So you will have a tank with your fluid like this. And then the idea is that you drop a ball of a known weight and area into it and then measure the time it takes to reach a certain point. When the ball is in the fluid, there are two forces acting on it. So you will have the weight dragging it down and then the drag force, which is preventing this motion. A few equations that we have developed in class are the coefficient of drag, which is as follows. Where mu is the viscosity and u is the velocity of the ball as it moves through the fluid. Another equation that we have seen is the drag force, which includes this coefficient. And once we sub this in, we can get Ft equals mu pi r times u. When the ball reaches a constant velocity, we know that the sum of forces has to be equal to 0. So the weight is equal to 6 mu pi r u. And then solving for viscosity, we get viscosity is equal to Ru. As we can see, velocity and viscosity are inversely proportional. So as velocity increases, viscosity decreases, and vice versa. For my kitchen setup, I use this bowl that we can see in the picture, and I filled my mason jar with tap water first, and I measured with a ruler the distance that the ball would be traveling. So for this, I got, for my distance, I have 0.14 meters, and then my time measured with a chronometer was 0.32 seconds. This gave me a velocity of the ball through water of 0.4375 meters per second. When the same thing was done with this soap, as was my selected fluid, the ball took a little bit longer. So the distance the ball traveled in dish soap was 9 centimeters, so 0.09 meters, just because I had a little bit less dish soap than water. And then the time it took was 0.73 seconds. So this yielded a velocity through soap of 0.1233 meters per second. This proves that water has much less viscosity than soap, as the relationship we saw before shows us that a higher viscosity, as is the case of water, will yield in a lower viscosity. So that is the viscosity of soap will be greater than our viscosity of water. Now, for the second part of this assignment, we had to create a non-Newtonian fluid in the kitchen. So, non-Newtonian fluid is that which changes viscosity with stress. So, it changes with stress applied. A few examples of this are some experiments that we've seen since we were kids. So, cornstarch and water, which when you hit it, it acts as a solid, but then when you pick it up with your hands, it runs like a liquid. And one that Dr. Fanak mentioned in the lecture would be whipping cream. So when you put whipping cream on the surds, it has kind of like a solid consistency, but when you apply pressure on it through the can, it flows, kind of like a liquid, or with more liquid properties. So something that I thought would also show these properties would be Jello. So for my experiment, I first made the Jello, as we can see in the pictures here. So first, I had to make the Jello by adding the water to the powder. Then we stirred it, and then we left it in the fridge for a little bit and checked that it was solid. Then, to check its flow properties with applied pressure, I put it in a Ziploc bag. And when we first have it on its own, it doesn't fall. As we can see here, there's nothing in my Tupperware. But once I applied pressure with it through my hand, the Jello flowed through the bag, showing more liquid-like properties, as we can see here. So this confirmed that Jello is indeed non-Newtonian, as it shows the different properties depending on the stress applied. This is it for my presentation today. Thank you very much and have a good day. Bye bye.